If we use welding parameters suited for metal, on the other hand, with a low melting point, you may cause lack of fusion defects on the part with the higher melting point. Another thing might be the differences in thermal conductivity. Metals like copper, aluminium transfer heat quickly from fusion zone, which cause high risk of welding defects, such as lack of fusion. We also see metallurgical problems, that is, problems with the metals in the melting zone or in the heat affected zone. Brittleness caused by intermetallic phases, that is, metals combining in a way that causes brittleness in the weld metal. We might have reduced ductility caused by precipitates. It's not strictly brittleness, but say a bending test, there would be problems if we have too much precipitates. That might be carbides or nitrides. And we might have solidification cracks due to segregation in weld metal, and differences in the necessity or respond to weld preheating. I mean, one material would need preheating, and another one would definitely suffer from too much preheating. And if we try to combine them, we need to find a compromise. And the same goes for post-weld heat treatment. Some metals would need it, and others would suffer poor properties after the same heat treatment. We see differences in thermal expansion coefficients, which might lead to a thermally induced fatigue. And it's not a problem during welding, but in the applications afterwards. If temperature is going up and down, the two parts don't follow each other exactly, and we might get cracks in the weld or next to the weld, depending on what is the weakest point. We could have differences in corrosion resistance. Two metals with different corrosion resistance in the same environment. There might be one which is noble, causing the other one to corrode faster than it would by itself. In the structure itself, in the weld, we might have or get phases that are sensitive to corrosion formed during or the solidification. And also we have residual stresses around a weld, and some corrosion phenomena are related to these stresses. And of course, if we have items which have not been welded, then we don't have the stresses, and there's less risk or less form of corrosion. An example: if we try to weld aluminium and iron or steel, we have a high risk of intermetallic phases. If we do it theoretically, we could go to phase diagrams and see that this combination of metals have areas where we have these intermetallic phases. So we can predict that if this is the combination range that we are in, we might get problems. And these phases are causing brittleness in the weld metal. Titanium is another metal which is problematic to weld to other metals. It's almost impossible to weld titanium to other metals by conventional welding, fusion welding. We get brittle phases with most other metals. If we, as I have read, I've not tried myself, but if we weld a titanium part and using stainless steel filler metals, we can hear cracks forming, creating noise during welding. There are some metals that we might be able to weld titanium with, or two. That could be zirconium, tantalum, or niobium. And we do see that some problems with dissimilar welds, including titanium, is controlled by using tantalum as a buffer layer, but it's very rare to see it and be done. Some examples of welding titanium to an iron nickel cobalt alloy. You can see the cracks have formed due to the brittleness. A lot of research is done on trying to solve problems by laser welding, because the process is faster and the amount of material melted is less. So that might solve some problems. And in this our example, we have titanium to aluminium. And from first glance, it looks like we have got a joint. It sticks together, but when we look into the structure in the weld zone, we can see some very odd faces around here, and I would certainly expect this to have poor mechanical properties. So it sticks together, but as a joint, it might be limited in application. A similar example for aluminium to copper. It appears as if we have made a joint, but when we look into it, the border faces are cracking, and we can't put any loads on a joint like that. It will crack or go apart. We also have copper to iron, which is giving problems with solidification cracking. In this example, we have a crack along the center of the weld. Some of you might recognize it as similar to hot cracks that we see when the surfaces are contaminated or the material is high in sulfur. Here we have made a similar crack by increasing the copper content. In fact, it's a sample that I've had made myself. It's a steel plate with another small part of steel on top of it, and between those two, 1 millimeter sheet of copper, and welded together, we get these nice cracks. A question? No. Okay. Laser beam welding of stainless steel to copper. Again, we can see that we have succeeded in welding, but the properties of the joint is poor. We have cracks in the weld metal, which would probably release a fracture if loaded to a high load. General remedies to the meteorological problems. Some problems might be solved by choice of filler material. Throw the weld pool composition away from the risk of having intermetallics or solidification cracking or what the problem might be. And a well-known example of that is welding stainless steel using the Scheffler diagram. It's a small one over here. We will return to it shortly. Or it could be using a nickel filler for the welding. Nickel is very much able to contain other metals and impurities, and by that avoid having problems. We could also, the reason why laser has been researched into, that if we can select a process and welding parameters to minimize segregation, then we would have less problems. The fast solidification works against having sulfur or whatever is causing problems concentrate in the solidification. We have more grains and more grain boundaries to distribute the impurities on. or we can use processes where we avoid or minimize the amount of melting of this sensitive or problematic base material. Example of that would be soldering or bracing, or even weld bracing. An example is MIG bracing, where we use the weld torch as heat source, and we use a filler metal, which is a bracing metal. We could also use friction welding, where we don't melt the material, but only have them mechanically bonded in the friction. Solid phase welding, or a process which is related to that, the explosion welding. Or, of course, we could avoid welding at all and use mechanical joints or adhesives. So to list some of the processes that we might choose between would be arc welding with compensating filler buffer, as we just talked about. Weld bracing might be MIG or TIG. It could be CMT, which is a process some of you might know, the cold metal transfer, which is a MIG process where the formation of filler material is controlled so that we transfer it at the lowest possible temperature, but still above what we see in shortcut welding. Explosion welding. Friction welding includes the friction stir welding process, which we will also look into shortly. Ultrasonic welding is used, some of you might know it from welding of plastics, but there are some specific welding jobs which is made by ultrasonic welding. I've seen very thin foils welded for electrical switches where they use ultrasonic welding. Diffusion welding, again, a very special technique where you have very smooth surfaces, very clean surfaces, pressed together and increase temperature. Atoms at a certain level of temperature, atoms would jump from one side to the other, and that way we will have a weld. It takes vacuum, and it takes high temperature, and it takes time. So I think this is a research technique. I've seen very few examples of this kind. Electron beam welding, where we have an electron beam as a heat source, was popular for very deep, very narrow welds previously, but as it has to be performed in vacuum, you can only weld a certain size of items, and you need to do it like a batch to get vacuum to get to normal pressure for each batch. So the area where electron beam welding was used is, for the most part, solved by laser welding, laser beam welding today. Having more power, we can almost do the same as in electron beam welding. And we also have laser hybrid processes where we can act more filler material from, say, a MIG process, and have the laser give the high heat power source. Example of welding stainless steel. We have the Scheffler diagram, and we could define some problematic areas from welding different kinds of stainless steel, or even low alloy steel, which would be like this. It's a diagram where we have the alloying elements which would form ferrite in the chromium equivalent. The more of that, the closer we get to the full ferritic material. And over here we have the nickel equivalent, the elements which would support austenite. And by that, we can calculate a position in this diagram for a composition welding one material or welding several materials together. And if we're in this area where we have the fullic austenitic solidification, the risk is that we could get hot cracking. And in this part over here, where we have low chromium and nickel equivalents, the risk is that we get martensite, which is hard but brittle structure. In the fullic ferritic material, we experience poor toughness due to grain growth during the welding process. So we don't want to go there either. And in this area, we have intermetallic phases forming. So it leaves us with this small area or window where we prefer to be when we weld stainless steel. And if we look into ordinary types of stainless steel, they would be in this area. And as an example, if you try to weld a stainless steel in this area with a carbon steel as the other part, a black and white weld, then obviously if we just melt the two, then the combined composition would be somewhere between these two in an area with martensite or perhaps martensite with a little austenite and a high risk of getting cracks. So we don't want to be in that area. We want the weld metal to be here like the stainless steel itself. So we need to choose a filler material which could drag us into this area. And we can do that by using a filler like the Arista P5, which is a 309 type of filler material. By that, we can sort of get the combined weld metal into the preferred area in here. And using nickel fillers, it's a choice for hard to weld alloys, cast iron, dissimilar welding, because it has this high solubility for, among others, carbon and the impurities. So a lot of the problems that we might experience from these combinations, we can solve by using nickel filler. But if we go back to to this diagram, we would see that nickel equivalent is high because it's directly related to the nickel content. We would be high up in this area, which means if we go one step back further, that we have to deal with a high risk of hot cracks. But that can be done by the groove design and the weld process itself. An example here of a filler called 4061, welded with TIG, with argon or helium or mixtures of those as shielding gas. We can use MIG or TIG to weld it, and we get strength in this level. So that's a filler material which can be used to solve some problems.
Sorry,
yeah.
I have one question. Hello.
Yes.
Thank you. I want to begin by just thanking you very much for this really informative, like class. But could you go 3 back? There was a graph on the lower right. Yeah, that one. And like 1 back, 1 forward. Oh,
this one.
Yeah, on the lower right. What are you explaining exactly?
Oh, that's the explosion welding. Sorry, I got by that a bit quickly. It's the way that explosion welding is performed. You have a base material, you have some flux in between, and then the other base material, and then you have an explosive that you ignite, and the explosion or combustion of it would get a pressure which sort of hammers the upper metal against the lower one, causing a friction weld bonding between the two.
Thank you so much.
We'll get back to an application of this process shortly. An example of using nickel as a buffer layer when you welding copper to steel. Nickel would be fully weldable to the steel side and also to the copper side. So if we buffer the steel by nickel, or both steel and copper, and then make a joint with the nickel in between, then we can join these materials.
Sorry.
Yeah.
So one thing, Gísli, getur þú tekið niður höndina? Ég vorst ekki að spyrja. Okay.
Sorry?
I was just telling him to take down the hand, so we are not expecting him to be make some questions.
Okay.
No problem. Okay, thank you.
Thank you.
Sorry about that.
There has been made or developed other filler materials, especially for this combination, like the copper aluminium or copper nickel filler materials, which could be used. And of course, we talked about the heat convection or conduction from copper, so we need to point the arc between or against the most conductive metal, which in this combination is the copper. And laser welding with copper silicon filler has also been attempted. And for an application using the explosion welded combination of steel and aluminium, the transition pieces used to combine or to weld together like ship hulls and the what you call the upper part of the ship, which might be in aluminium. As we started to say, you can't weld them together directly, so you need to have some transition between them. And you can use the explosion welded plate, cut it into bimetallics, they are often called in English, where you have the steel, the aluminium combination layer, and the upper part also aluminium. And then you can weld steel to steel and aluminium to aluminium. It's also exemplified in this where you can see the steel, the pure aluminium as an intermediate layer to have these alloyed aluminium on the top, one with more strength and more corrosion resistance. And these have been explosion welded together as a part you can buy for making this combination. I also mentioned friction stir, which is a method which is in use for aluminium, to join aluminium parts. It's the friction because you have this rotating pin which sort of rub the material together. You have to imagine that the pin is going down into the metal, and by the friction between the top chest and the pin, you rub the material together in a friction weld. There's no melting, so that way we don't get the solidification problems and the intermetallics forming in a melt. And we can combine the materials and have cross sections like illustrated down here. Combination of different metals is tricky because the deformation properties are very different in a steel and an aluminium. but I know research is going on both to use this process for further than aluminium, but also for combination of different metals. In this, it has attempted to do the aluminium, two different types of aluminium in a friction stir welding. An example of laser MIG hybrid welding, where we have a filler material through the MIG torch, and we have a laser as a heat source to melt the filler metal, and that way we could combine aluminium and steel. The result is shown over here, where we have the steel part and the aluminium and the melt between them. As we often see in aluminium, we have some porosities, but the fusion between the two, and the steel is sufficient. These lines indicate what we would measure to sort of control the quality of the weld. How is the wetting length, top and bottom? On the aluminium part, there's no problem, of course. I was also asked to say a little about corrosion and the effect from welds on corrosion. And to start with corrosion itself, it's a process where we dissolve a metal. And to have that process running, we need to use the electrons formed in this process need to be used in another process. Otherwise, it will stop after some time. It would be saturated in the electrolyte in the environment here, and will almost go to a stop. But if we have another process which is using the electrons, then we have the corrosion cell going on. And the electron consuming part is oxygen, or it could be hydrogen. So we need to have this process, what we call the cathodic reaction, to have the dissolution of metals in the anodic reaction go on. And if we don't have these two processes in the same environment, same electrolyte, then it doesn't go on. And if we cut the quartz, the lead between the two, then it will also stop. We also need to see what happens when corrosion starts. Does it go on like this, or does it form some kind of protection? And the ultimate protection is to have a passive layer on the surface. If we have a dissolution, it might go with the extent of corrosion over time like this. There's a little protection from rust as an example. So the rate is going down, but it will still corrode a lot. But if it forms a layer on the surface, the corrosion products itself forms a layer which protects, then we will have an initial corrosion, and then it would go to a very low level. That's what we see on stainless steel. We still have a little corrosion over time, but when it's so little that our equipment would last for thousands of years, perhaps, then we considered it as sufficiently resistant. So we have this layer of protection on the surface. But when we have welds, there might be several problems with this resistance from passive layers, and other problems too. If we have two materials with different galvanic nobleness, then we will have corrosion between the two. An example might be this part which has been in a pickling bath, an acid, where we can see that some parts were less noble and disappeared in the acid. and this one also to some extent. We could have that there are differences in the microstructure, and often that would be related to differences in the composition from solidification in the melts, segregation, formation of precipitates, which would be more or less noble compared to the base structure. We could lose alloying elements. Some of those who should give us corrosion resistance could be lost during welding, oxidized away, evaporated, or burned away. So we need to compensate that. We'll often see that the weld metal is higher in alloying to compensate for this loss. We also have a problem with some combination that we could get sensibilization, which means that the material gets sensitive to corrosion from change in microstructure during welding. Grain growth could also affect corrosion properties of the material and the problems that we would see in the heat affected zone. And also welds could have geometrical crevices from the design where we would have overlap which would give crevices, or we could have weld defects causing crevices. And most materials, depending on a passive layer for corrosion resistant, so would be very sensitive to crevices. You can't keep the material passive in a crevice over time. It will lose the passive layer in the crevice. And also, if we have talked about before, tensile stresses, residual welding stresses can cause problems. And the surface finish in and around a weld would also affect the corrosion resistance. Oxides on the surface have an effect. And of course, the example up here in the corner, poor weldmanship would also mean that this is more sensitive to corrosion. Any deposits, contamination would stick to this weld very easily and might cause problems. To get a little overview of different problems with welds, we could have that the weld metal itself is not as resistant as the base material, causing selective corrosion of the weld metal. We could have selective corrosion in the heat affected zone. That would be a risk if we have a very noble weld metal and no protection of the material. Then the part closest to it would be sensitive, or it could be the precipitates grain structure in the heat affected zone, which caused it to be more sensitive to corrosion. We could have what's called intergranular corrosion, which is corrosion around the grain boundaries in the metal caused by the heat from the welding, and it would often be a little away from the fusion line compared to the heat affected zone. Some metals could cause knife line corrosion, which is sort of HAZ problem, but only along the fusion line. In low alloyed steel, it would be related to too much sulfur in the material, and in some stainless steel with titanium or niobium, it could be something about the carbides dissolving and forming during the welding process. Or we could have stress corrosion cracking from the residual stresses, and perhaps also when you have this cap on the weld, you would get some stress concentrations along the top, and by that increasing the stresses and the risk of stress corrosion cracking. And for the same reason with the stress concentrations, we would also see that corrosion fatigue could attack along the wells. It's ordinary fatigue, but with increased sensitivity and growth rate due to corrosion. An example of a bit old example, perhaps, of selective corrosion in a weld metal was an icebreaker, which was sailing in the north part of the Baltic Sea, and shortly after being taken into service, it was found that the welds were disappearing by corrosion, illustrated by this sketch here. And it's not this one, but I don't actually have a photo of the actual icebreaker. But the reason for the problems was that there was used a basic electrode with a relatively high amount of silicon and manganese, which caused some hardening elements in the microstructure, which would be noble to the structure around them, and by that the weld metal were losing its corrosion resistance. And of course, the ship hull was painted, but especially a problem for icebreakers that the paint would be eroded, worn away by ice opening for corrosion in the steel and the welds. If we should go to minimize the amount of silicon and manganese to avoid these sensitive microstructures, we could look into what should I call it? A very ordinary rotile electrode like this one, just as a thought. But in the end, it would have too low strength and probably also too little impacts toughness for this application. What was done, as I recall, was to increase the alloying with a little nickel to get an overall higher corrosion resistance of the weld metal. For higher alloyed materials like stainless steel, we could define a relative factor for their corrosion resistance, and it is defined in a lab testing environment called ferric chloride. And in a logarithmic diagram, we could get a straight line for the relation between the alloying and the temperature where it fails. The critical pitting temperature, by using this what do you call it, formula? No, it's not called that. Where we have chromium 3.3 times the molybdenum content plus 16 times the nitrogen content. So in the base material, we would see that increasing this parameter, we would increase the corrosion resistance by the CPT, the critical pitting temperature. But if we melt the material in a weld, autogenous without filler material, then we would see that it follows this line, a little below the base material. The finer the microstructure in the solidification, the faster the process, you could say, the closer these are together. And the larger the weld pool you have, the more segregation, the more they will be apart. But when we reach a certain level of alloying, then we can no longer have weld metal with resistance which is comparable to the base material. And we have the stainless steel called 904L just about here, where it sort of divides between the two. And a high alloy stainless steel like 254 would be in the area like 44, 45 in here. And if we weld without filler material in this, we would get a very sensitive weld metal. So in fact, we compensate. We use an Inconel 625, which is up here, to weld in order to get that even the most sensitive parts of the weld metal would be comparable or above base materials properties. So we need to compensate for segregation and microstructure differences to avoid corrosion. I mentioned intergranular or intercrystalline corrosion and sensibilization, and it's something related to the carbon content of the stainless steel. If the carbon content is too high, heat from welding might cause precipitation of chromium carbides, and they will form on the grain boundaries, because it's easier for carbon especially, but also for chromium, to diffuse on the grain boundary. So it's easier to get enough to chromium and carbon to form carbides. But when you drag chromium into carbides on the grain boundaries, then you might risk that there's not enough chromium left to secure the corrosion resistance in the areas along the grain boundaries. So that gets sensitive to corrosion. If you say we have like 18-20% chromium in the grains here as the average composition, then we might get as low as 10 to 12 in this area. So obviously very much less resistant. And we have two ways to avoid that, or in fact we have three. If we can weld fast enough so that we don't get so many carbides, then we also reduce the sensitive areas around them. But if we don't, we will have a situation like this, where grains would fall out due to corrosion along the grain boundaries. Or we could reduce the carbon content. We have a diagram here, which is in fact the results of corrosion testing, where we can see that heat treatment, say at 800 degrees C on a carbon steel with 0.08, would cause that the material would fail in a corrosion test in about half a minute. And that is, in fact, what you get if you order, or you might get if you order a 316 or a 304 stainless steel on an icy American standard. Then the limit they could give you is 0.08. But if you choose for an L grade, 316L, 304L, then the standard says there must be no more than 0.30% carbon, and that gives you 8 hours before it will fail in a corrosion test, and the level is 600 degrees C. But the crucial thing is that you get so much more time from the reduction of carbon. Another way to do it, and especially in Germany, it's the preferred way to do it, is to add titanium or niobium, which would form carbides, and that way reduce the amount of carbon which could make chromium carbides. So either a very low carbon content in itself, or addition of something which pulls carbon out of the material into other carbides, which doesn't affect corrosion resistance. We call them stabilized grades. I mentioned crevices, and of course this is not welded, but it illustrates a crevice from a flange towards a body. And this has been in seawater and the amount of corrosion is extensive. And in fact, it's all the way down here inside the metal from the seal phase here. But also a weld defect like this one, stainless steel welded without full penetration, gives us a crevice which has started corrosion. And this is in Danish domestic tap water. We have salt enough for causing this problem. The stresses we talked about could give stress corrosion cracking, which is a corrosion process combined with stresses which form cracks, which both are branched and which form very quickly. In the laboratory, we can make stress corrosion cracks grow like 1 millimeter per day, per 24 hours. But fortunately, in the actual world, it's not going that fast. But it is definitely a risk if we get into an area with sufficient salts and sufficient heat and sufficient stresses, then you have this kind of problems. And the relation to welds is perhaps not so obvious in this one. We have a weld, not a very pretty one, but just still a weld, and we have cracks going out from it. But in this one, it's very obvious that it is the weld stresses. There is a stiffener welded to the outside, and we can see how stress corrosion cracking forms around the stiffers at the weld, and it goes both around and perpendicularly to it, out into the base material. And corrosion fatigue, I don't know if you can see it, but we have a weld here, and we have a fatigue crack running along this due to vibrations in this part. And as I mentioned before, fatigue is one thing, but when you have corrosion on top of it, it will initiate faster and grow faster. An example here of fatigue in air without the corrosion, where we could have a stress level or amplitude of the stresses up to 380 or something like that in air. But if it's in a salt solution, it's not more than about 250. So it clearly illustrates how much difference corrosion does to fatigue, or might do. Pitting is, in this instance, related to oxidation. Oxidation along the weld. This is the internal side, the root side, and purging with gas has been attempted, but it has not been fully efficient. So we have pitting formation in this discolored zone, oxidized zone along the weld root. The reason why it's so extensive on this side is that it is 304 and this is 316. So if this was also 304, we would have expected this area to be attacked as well. The reason for difference between the two sides is probably that we have had the purged gas coming from the top and being heated over the weld, so that the reaction is faster on this side. In fact, this phenomena is the same as we saw with the carbides. We have a depletion, lower level of chromium, but not around carbides. Here it's below an oxide layer on the surface. The oxide is rich in chromium, and when it's formed, it drags chromium out of the material into the oxide, and you have a very, very thin layer. We're talking about μmeters below, which is sensitive. But once a crevice or a pit has formed, it will grow, even though it gets into sound material below this depleted layer. Do we get any help from the standards to control this problem? In some ways, but not fully. we have a standard like this one, EN standard 12502 part 4 for protection of metallic materials against corrosion and stainless steel. It says that oxide films and scales highly increase the likelihood of pitting. So a red flag is pulled up to say you need to be alert, to be careful. And if you have colors that are darker than straw, then it strongly increases the likelihood of pitting. So there is an indication that we have problems, but this standard doesn't say that you can't have it. It just says that you should be careful. And of course, if we don't have any protection at all, we will both have oxidation and would have heat tint also very much above the straw. And you can see corrosion has started. Again, it's just a humid domestic water application. But this is, on the other hand, a perfect weld in an electropolished tube for pure water and a pharmaceutical plant. Full protection with purge gas and a tick process, which is probably automatic as it looks like this. And we can not see any. The yellow here is reflections. It's in fact fully bright. But to have a tool to inspect if it's above straw or below, for many years since, we have had a reference, a report with reference pictures to sort of say we need to have something which is below the straw, and we defined by Corrosion Test that this was the limit. Above that, we would have sensitive surfaces to corrosion, and this one and below would be almost unaffected by the weld process. We have later on changed the pictures to in the old one we had some levels which we couldn't cover with pictures. So when we had the chance, we made new, but this time as point to or local wells, and we got several colors around it, but we can define that this is the sea level that we want, and this one is above, and the blue one is certainly above. So if we want to have a well which could be exposed to water with a certain level of salt in it, then we would need to have something which is below the sea. If we, on the other hand, would clean it by an acid, which it would be able to remove both the oxide and the chromium depleted layer below it, then we could accept up to this level. This could be removed and restored by pickling. But if we go to the highest level, up here we have a scale which it would take too long time to dissolve in the acid. So we don't recommend to go to that level. Even pickling is applied. This is just an illustration of the different problems we could have with contamination and oxides, and which would be cleaned away if we do a pickling. You see, the drawback of pickling is that you get on a microscale a more rough surface because the acid attacks the grain boundary slightly. So we don't have the same as a polished surface after pickling. But we can see the effect here that we have very good corrosion resistance when we pickle. If we only grind to get rid of the oxides, then we would not get as much. But the finer we grind, the better it gets, but still not the same as pickling to solve the problem. Just to mention that the references that we provide has also given an American standard. We were first, I could say, but some years later, the American Welding Society made a standard called 18.1 with reference picture like this, where you could define that you want your welds to be at level 3 or better. It appears that they are a little darker, but you have to be aware that the printer you use, the monitor that you look on would be slightly different. So in fact, the sample might be a little less red than this one in the actual world. If we want to test if our weld has succeeded, we could use a corrosion test. And a very popular one is the G48 test, which is using the ferrichloride, which we also saw on the graph earlier for the pitting temperature used there to define the pitting resistant equivalent, the PREN value. But here is the test solution we use, and after a certain exposure, you shouldn't see pitting. And we also have a weight. How much could this test reduce the weight of our sample? So there's two parameters. It mustn't reduce the weight too much, and it mustn't cause pitting corrosion like seen in this one. Oh yes, just to finish off, the effects of welds on corrosion protection by welding. Some examples: if we have a weld, there's of course the weld cap, which might give an uneven surface on the paint. So if it has been grounded, it would be a better surface on the paint. But still, there's protection. But it might lead to have contamination or dirt collect along the weld if you have too high a weld cap, and underneath this the paint might be challenged and corrosion could start. Worse if you have the contaminants or weld spatter or whatever slag on the surface below the paint, then the efficient or the effective thickness of the paint is very poor in some of these points, and you could get corrosion problems. So a smooth weld, clean from any spatter or slag or other residues or contamination, that's the best way to get a good protection from paint. Thank you for listening.